At this point, we're ready to talk about Cauchy's theorem, which is one of the central theorems in complex analysis. And what it says is the following. Let gamma naught and gamma 1 be homotopically equivalent. So they're going to be two curves that are G homotopic in a region G. So remember that a region is an open connected set G. So suppose that they're homotopically equivalent. And let gamma naught and gamma 1 be piecewise smooth. So they're going to be piecewise smooth curves. If f is holomorphic, in G, then the integral over gamma 1 is going to be the same as the integral over gamma 2. Now, I just want to talk about this for a second. I want you to really kind of sit down and think about this. This is a pretty deep theorem, and there's going to be a few corollaries which also sometimes go by the name Cauchy's theorem, but we'll talk about that in a minute. This says, first of all, if gamma naught and gamma 1 are homotopically equivalent with fixed endpoints, this is old news. We knew this. Because to be holomorphic means that you're differentiable and therefore continuous, and therefore you have an antiderivative. Every continuous function has an antiderivative, as we know from the fundamental theorem of calculus. If gamma 1, and I'm using gamma 1 and gamma 2 here, so just to be consistent with myself, I should call one of these gamma naught. But if these two curves, gamma naught and gamma 1, are homotopically equivalent as closed curves, so say we're back to the square and the circle example, this is still true. And that's a pretty remarkable theorem if you think about it. So of course, if you have the same endpoints, then we know by path invariance that we expect this to work out. However, this is still true if you have two curves that are homotopically equivalent, even if they don't have any endpoints in common. And so if you were to integrate over a square and integrate over a circle, as long as those two curves are homotopically equivalent in your set G, then your two integrals will be the same. So this is a pretty remarkable theorem. And it has as a corollary the following consequence. So I'll call this a corollary. Sometimes this corollary, somewhat confusingly, is also called Cauchy's theorem because this is oftentimes the version of it that gets used. But what the theorem says is the following. If f is, so same assumption on the function f, but if f is holomorphic, so it's going to be the same setup in G. And if, let's say, gamma is piecewise smooth and homotopically equivalent to a point, so and homotopically equivalent to a point, then it turns out that the integral of f over gamma is going to be the same as the integral of f over that point, which we know that an integral over a single point is going to be 0. So if you have a holomorphic function and you want to calculate the integral over some piecewise smooth curve gamma, and if gamma is contractible, meaning that you can homotopically map it to a single point, then the integral over that function must be 0. Okay, so again, this corollary is sometimes also referred to simply as Cauchy's theorem, but it's kind of a corollary of the stronger statement above. And then I want to tell you one more corollary. Okay, so one other corollary that gets thrown around. If f is entire, so if f is entire and gamma is any closed path in C, then of course the integral over gamma is going to be 0. Okay, so that's a legitimate corollary to the two previous results.